Swayam Prabha. Digital India. Educated India.
Welcome to the second lecture of module 2, which is on manipulation of STL files. In this lecture, we shall discuss about the orientation of STL files, how can we rotate or translate these STL files. Also, we shall discuss about the support structures, the different type of support structures and the zone where support structures are required. Also, we shall discuss about the optimal part orientation, and the optimal orientation of the part can be obtained by a cost model, a surface quality model and a minimum support model. Now, let us discuss first about the rotation of STL files. If you have a point in the Cartesian coordinate system x, y and z in 3D, and I want to rotate this object about x-axis. So, I am going to look at from this view and going to rotate this point about x-axis. So, a view from this end, if the observer is standing here, can be seen and it will look something like this. This will be your y-axis and this is your z-axis. Now, assume that this distance is L and the projection of this point on the y-axis will be y1. The projection of this point on z-axis will be z1. And assume that this line is making an angle alpha from y-axis. Therefore, the distance y1 will be equals to L cos alpha and the distance z1 will be equals to L sin alpha. These are nothing but the projection of this distance on y-axis and z-axis. Now, if the point rotates by an angle theta x about the x-axis, in that case this point will move to this red color point and this angle will be theta x. The new projection of this point on the y-axis and on the z-axis will be y2 and z2. Now, let us write z2. z2 will be equals to then the length L. This length will remain same because I am only rotating it. So, z2 will be equals to length L into sine theta plus alpha. Theta plus alpha. Let us expand this term and hence we will get z2 equals to L sin theta cos alpha plus L sin alpha cos theta. Also, we know that L cos alpha is nothing but y1. So, let us replace L cos alpha by y1. Hence, we have y1 sin theta here. Also, I can replace L sin alpha by z1 and hence this particular term is now z1 cos theta. So, z2 is equals to y1 sin theta plus z1 cos theta. In a very similar fashion, I can write the projection of this point now on y2, that is y2, and y2 will be equals to L cos theta plus alpha, angle from here to here. Now, let us expand this term and you will get y2 equals to L cos theta cos alpha minus L sin theta sin alpha. We have already seen L cos alpha will be equals to nothing but y1 and hence this term is replaced by y1 here, and also L sin alpha will be equals to nothing but z1 from this equation. Hence y2 is equals to y1 cos theta minus z1 sin theta. Now let us write the coordinates of this new point x2, y2 and z2 in terms of x1, y1 and z1. So x2 will be equals to nothing but x1 because I am rotating about x axis. So x2 will be equals to 1 x1 plus 0 y1 plus 0 z1. Also we have just derived this equation which it states that y2 equals to 0 x1, there is no x1 component here, plus y1 cos theta minus z1 sin theta. Also z2 equals to 0 x1 plus sin theta y1 and cos theta z1. I can write this system of equation in the matrix form like this, and hence the new coordinate of the point, those are x2, y2 and z2, on the left side can be written as a coefficient matrix multiplied by the coordinate which were earlier x1, y1, z1. This coefficient matrix is called as nothing but rotation matrix, and this is particularly here when rotation is about x axis. This matrix is 1 0 0 0 cos theta minus sin theta, 0 sin theta cos theta. In a similar fashion, if this point rotates about y axis, then the rotation matrix will be this. You can easily derive it now. And also if this point rotates about z axis, the rotation matrix will be this. Now you have all the rotation matrix. It is very important to note one point here, that the sequence of rotation is also matter. So for example, if you are rotating about x axis first, then about y axis and then about z axis, or you are rotating about y axis, then z axis, then about x axis, the results will be different. So basically, if I am just writing it, x2, y2, z2 equals to this sequence first. So first rotation about x, second rotation about y and third rotation about z. It will be written as r theta z into r theta y x into x1, y1, z1. It is only when this sequence is followed. If the sequence is something else, then I need to write that sequence. So for example, this is first, this is second, this is third, then r theta x dot r theta z, r theta y and x1, y1, z1. So this is how you can rotate any point in the Cartesian coordinate system. And we know that the triangles of the STL file are consisted of nothing but the 3 points only. So let us extend the same analogy here. The coordinates of the rotated point can be given by this equation, where pikx, piky, pikz are the coordinates of kth vertex. There are 3 vertex in a triangle, so these are the coordinate of kth vertex of ith triangle. As there are number of triangles, I am talking about ith triangle. The I can vary from 1 to 2 to 3 to n, where n is the number of triangles to represent the solid. In the similar fashion, the normal of the triangle can also be rotated. The normal of the triangle can be rotated, and the equation for that is written here. This is the new normal and this is the old normal multiplied by the rotation matrix, whether about x axis, y axis or z axis, any one of them, where NIX, NIY, NIZ are the coordinates of outward normal of the ith facet or ith triangle. In a similar fashion, you can do the translation also. As the triangles of the STL file are consisted of nothing but 3 points, the whole thing will move. We need to just add the vector corresponding to the translate. If this triangle is moving like this in any direction and it moves x, y and z in the different components, then the new points will be nothing but represented by this equation, where, as I have already mentioned, pikx, piky, pikz are the coordinates of the kth vertex of the ith triangle, where n is the number of triangles. In a similar fashion, the normal will not change now because you are just moving. In a similar fashion, the normal will not change now because you are moving the whole thing, and hence contact normal is not going to be changed. You can see that example. If this is my object and this is the contact normal of a facet, now you just translate it. The normal direction is not going to change. You go in any direction, the normal will always in this direction, and as it's a unit vector, definitely it is not going to change. But if I am rotating, you see that if I am rotating, then the contact normal will also change. Now let us see a small MATLAB code which I have written to read the STL file and to manipulate it. Here I have created a function which is known as import STL, and it imports the STL file in the ASCII format. You now also know each and every line which is written in the ASCII format, and appropriately you can just read the STL file. It is a very easy task. The file which I am going to import is known as cube.a.stl. It is a cube which we have created in the last lecture, and if I will not rotate this STL file, it should look something like this. So this is your cube. It is consisted of the 12 triangles, 2 on each face of the cube. How it is reading? I am storing the data in this format. First vector is P. I am storing the data in this manner. This first matrix is P. The P matrix stores the x, y and z coordinate of each and every vertex. Also, it stores only the unique vertices. Those are shared with multiple triangles. Later on, appropriately, the topology is defined. This avoids the repetition of the multiple points in storing, and hence your code can really work very fast. Then this vector t, which defines in this triangle which particular vertex is assigned, and then the normal of the triangle. So for example, I am representing this STL file through this code. This particular vertex, it is shared by this triangle, this triangle, this triangle and this triangle. Therefore, I am storing this vertex only once. So this vertex is common, and hence I am just telling that how these triangles are formed. In this way, you can save really a lot of redundancy in the STL file. So all these points, those are here, I want to rotate. So it is very simple. I'll just define a rotation matrix. For example, I want to rotate this cube by 45-degree angle about x-axis. So this theta x I have defined as 45, and the rotation matrix which we have just derived is written here. Now if I run this code, you will see that the cube has been tilted by 45-degree in counterclockwise manner about x-axis, and this is how it looks like now. You can even rotate it about y-axis as well. Let me just show you. If you rotate it about y-axis, how does it look like? Now I am changing the parameters. There is no rotation about x-axis, only there will be rotation about y-axis, and that is 45-degree about y-axis. And hence your STL file will look something like this. So it is very easy. Now only thing I am doing, I am just multiplying. You see that here in this loop I am just multiplying the P with rotation matrix, means the all the vertices of the STL file with rotation matrix, and hence replacing the new vertex by this multiplication. If I want to rotate about y-axis, the same thing is done here. You can also translate your object. For translation, I have defined a vector here t, and if I want to move this particular object by 100 mm and don't want to do any rotation, so let me remove the rotation from here and run the code. You have seen the whole cube has moved. The cube looks like cuboid because the axes are not of same size, that is why it looks like a cuboid, but it is still a cube. But it has moved now. You see this particular point, the first point of this is not 0, 0, 0, it is 100, 0, 0. And the last point is of course 200, 0, 0. Also, we can multiply the rotation matrix with the facet normal also, like written here, T norm equals to T norm into rotation matrix Rx. If it is rotating about Ry, means about the y-axis, then it is multiplied by y-axis, and hence you can multiply and rotate the normals as well. Now let us discuss about the support structure. The support structure is mainly required while creating the overhanging features in the STL files. In some additive manufacturing processes, the explicit support structures are not required, such as in the case of binder jetting and powder bed fusion, particularly sintering, the remaining loose powder act as a support material and later on can be removed also easily. However, in some additive manufacturing processes like FDM, DED, material jetting, the support structure need to be created in during the pre-processing of the CAD model, and later on in the post-processing the support material also has to be removed by some means. An example of the support structure is shown here. This particular part, when it is built in this direction, this is the build direction, this portion is overhang portion, means here the support will be required to create this part. Otherwise, this particular portion when we are creating may fall down. So these are the support for that. If I change the orientation of this object, you can see the support is required only for this zone. And if I further rotate this object, you can see that no support is required at all. You have already seen how to rotate an STL file. So we need to sometimes rotate the STL file in such a way that we can eliminate the support structure at all. And it is quite possible in some cases. The support structure is basically a sacrificial material added to support the overhanging features. There are other types of sacrificial materials also used in additive manufacturing, and those will be discussed later. Now, for a given STL file and build direction, the support structure can be easily calculated based on the facet normal of the triangle of STL file. If you see this particular triangle here, this is the build direction. Assume that plus z is the build direction. You are building the object in the plus z direction. Then the triangle, those are having normal pointing upward, will not really require the support material, but the triangle those are having the facet normal downward may require support material. Again I said may require. We will discuss about this word, why I am saying that it is not always required. So if you are building the part in plus z direction, like I said, let us consider the three different cases. Here the facet normal is upward. Therefore, definitely no support will be required for this particular case. In this case, facet normal is downward. And in this case, facet normal is again downward, but the angle theta is much larger than this one. Okay, so this theta is much larger. Therefore, in this case support will be required, and in this case support may not be required. Let us see when support is really required. Each additive manufacturing process deals with different type of materials, and different type of materials can sustain some overhang. Beyond a certain limit, the droplets or the molten material may fall down. Let us consider a case where it is required to build this particular wall, and it is having a certain amount of overhang. The facet normal everywhere which is same is downward like this. In this, if the layer thickness is capital T, the overhang is D. Overhang is nothing but this distance from here to here, material which is not supported anywhere, while this material is supported on the pre-built layer. If I reduce the thickness of the layer, of course you can see for the same case the overhang amount will reduce to small d and layer thickness will also reduce to small t. In that case, let us now consider that this is the face which we want to build and this is the contact normal which is having an angle theta from the build direction, that is plus z. You are building in plus z direction. This angle is from here to here. Now, if this angle is theta, let me consider this particular triangle. Of course, we know that this angle will be nothing but pi minus theta. If this angle is pi minus theta, then of course in this triangle, this angle will be pi minus theta. Now you can use simply this right triangle, tan pi minus theta equals to T by D. Hence theta equals to pi minus tan inverse T by D. Therefore, if the angle alpha between the build direction K and the triangle normal N is greater than theta, the support will be definitely required. Meaning to say, if this angle, for example, this wall is tilted like this, for example, in that case your contact normal will be this or the facet normal will be this, and this will be the angle greater than theta. Hence, you need support mechanism. Let us find out what will be that angle first of all. So, this angle alpha, assume, will be equals to cos inverse the dot product between the contact normal and the build direction which is z direction here, that is why k is written here. Hence, alpha will be equals to cos inverse the z component of the contact normal, where of course nxi, nyi and zi are the coordinates of the outward normal of the ith facet. Now, let us solve a problem to find out the critical value of this alpha. It is given that in an additive manufacturing process, the maximum possible layer overhang can be of 1 mm. So, the overhang which was unsupported by anything is 1 mm. So, D is 1 mm. The build direction is plus z, we are building in this direction, that is plus z direction. The minimum possible layer thickness is root 3, that means the minimum possible layer thickness root 3 is given to you. Find out the critical value of z component of the facet normal of the triangles of an STL file. Beyond that, the support will be required. So, let us first find out the theta. Theta will be equals to 180 minus tan inverse, it is given to you that T is nothing but root 3 and D is nothing but 1, and hence this will be nothing but 60 degree, and hence theta will be equals to 120 degree. That means if this is the build direction, and this is the facet normal. This angle is 120 degree. If this angle is beyond 120 degree, for example, for the lines like this, the contact normal will be this, hence this angle is beyond 120 degree, the support will be required. For no support, alpha should be less than theta, means this angle alpha should be less than theta. For the critical cases, alpha should be equals to theta, of course, and hence cos inverse the z component of the normal will be equals to 120, and hence the z component of the normal is minus 0.5. Hence, if support is required, this particular component will be less than minus 0.5. If it will be less than 0.5, this angle will be beyond 120 degree and hence support may be required. You can very easily identify these triangles in the code which you have written in MATLAB. For example, this particular STL file, if I say that, if I apply the same rule which we discussed in the last problem, that the facet normal, those are having angle greater than 120 degree with the plus z direction, which is the build direction, are highlighted here in yellow color and will require the support material. So this is the component, and if I tilt it, I just rotate it just to view, you see that these yellow triangles, they are having the contact normal which is greater than 120 degree. These particular triangles, of course, are going to have just vertical downward, and hence they are having 180 degree angle, and definitely it is greater than 120 degree. So support is required. For these blue triangles, support may not be required. For example, this particular triangle is having upward normal. It's not requiring any support material. This particular triangle is having 90 degree angle from the z axis. Hence, it also doesn't require the support material. Till 120 it can support, but beyond that it will not support. Let us see the same thing if we apply in our MATLAB code. So here I am going to give different color to the normals. This T normal is the vector which is storing all the normals and corresponding triangles. If this value is less than 0.5, which we just calculated, let us assume if it is less than minus 0.5, the z component, the third component, if you see that 3 is written here, the third component of the contact normal, if it is less than minus 0.5, the color will be this, which is written 1, 1, 1 here, and if not, then the color will be something else. I am also counting these triangles, and I will show you if I rotate the object, these numbers may change. So let us consider the cube case first, and I am not going to rotate it or translate it in the beginning. In that case, if you see, these bottom two triangles are going to have 180 degree angle with the build direction. Therefore, these two triangles will require the support material. In a similar fashion, now rotate it by some angle. Let us rotate it by 45 degree about the x-axis, and you can see these triangles will require the support, and also these two triangles will also require the support now, because they are now actually making an angle of 135 degree now from the build direction, which is definitely greater than 120 degree, and hence both the triangles are requiring the support, and therefore all four triangles are requiring now the support. So just by changing the orientation of the object, you can see that the support can be increased or decreased. Let us consider an example of a sphere now. I have a file in the folder which is named as sphere ASCII format and fine triangles like this. And I am going to open this. It will take few seconds, and you can see that all these yellow triangles, those are visible here, will require the support now, and the blue triangles will not require the support. I can change its value if I change the threshold. If I say that this value, if it is less than minus 0.1, then the zone where I was getting the triangles will increase. So you can see that now the zone where I am getting the yellow triangles, means the triangle those require the support, has increased now. And if I make it like less than 0, all the triangles those are greater than 90 degree will require the support, and the zone will be exactly at half of the sphere. So this is how you can easily identify the support material or the triangles corresponding to the need for support material easily in an STL file. So this is how all the CAM packages of additive manufacturing works. You can appropriately orient your object in such a way that you can minimize the support. However, there are three different ways of optimizing the orientation of the part. One is the cost model, another is minimization of the surface roughness model, and the last one is, which is very easy and straightforward, minimization of the support structure model. Let us discuss now about support structure. If, for example, someone wants to build this part by additive manufacturing and this is the build direction, then in that case no support will be required for this particular part. However, if you change the orientation of the part, then you will realize that the support will be required for some of the features. Like if I tilt it like this, then you can see this particular part, when we will build, it will require some support. To give a support to this particular region, we need to provide some structure that is called as support structure. And later on, when the part got cured, the support can be removed and it can sustain. So this is the basic of support. So how do we identify the region where the support is required and where the support is not required? We have already discussed the facet, those are having downward facet normals, usually require the support mechanism. Also, we have seen that there is a threshold beyond that value we really require the support mechanism. If we have identified the triangles which requires the support, now the question is how do we generate the support to support these triangles? So there are two ways of generating the support. First is called as support generation from the facets. The support from the facet is generated by considering the project area of the triangles on a plane which is perpendicular to the build direction. So for example, you are building in this direction and there is a triangle here. This particular line is perpendicular to a horizontal plane like this. Then we need to consider the projected area of this on the bottom, and that will be the footprint of the support. This part will now get protruded till the facet. The question is now how do we find out the projection of a triangle on a plane? For example, a triangle is consisted of 3 points, point A, point B and point C, and we are building in a direction which is not really vertical but any random direction, and the perpendicular of that surface is given by nx, ny and nz. Now our objective will be to find out the projection of each 3 point on this plane which is perpendicular to the build direction. Now let us consider that first our point is A, it's having a coordinates x, y and z, and this point is going to projected on this plane which is perpendicular to our build direction, and the projected point is A dash. Its coordinates are now x dash, y dash and z dash. The equation of this plane can be given like this. This is nx x plus ny y plus nz z minus a equals to 0. Now let us try to find out the value of x dash, y dash and z dash. So first of all, let us find out the equation of a line A dash that is passing through a point x comma y comma z and it is parallel to a vector. And the line is parallel to a vector which is nothing but the unit normal nx, ny and z. Hence, I can write the equation of line in 3D, you already know that, like this: x minus x by nx, y minus y by ny, z minus z by nz equals to alpha. It is a constant. Now, this line will also pass through, the line AA dash will also pass through the point A dash, as point A dash lies on this line. Therefore, the point x dash, y dash and z dash should satisfy this equation. Now, let me put this value here and replacing x by x dash, y by y dash and capital Z by z dash. And hence, you will have x dash minus x by nx, y dash minus y by ny, z dash minus z by nz equals to alpha. Now, I am giving a number to this equation as equation number 1. Also, point A dash lies on the plane on which we are trying to get the projection, and the equation of this plane is given by this equation. Therefore, if I put this point A dash into this equation, it should satisfy it because A dash is lying in this plane. Hence, the equation will now become nx x dash plus ny y dash plus nz z dash minus A equals to 0. That is my equation number 2. Now, let us find out the value of this alpha by using these two equations. It is very easy, that we can do easily by replacing x dash in this equation, in equation number 2 from equation number 1. I can write x dash equals to alpha nx plus x, like here. Similarly, I can write ny equals to alpha ny plus y and z dash equals to alpha nz plus z, and hence this is my equation number 3. From this equation, I can easily find out now value of alpha because that is the only unknown here. Once I know the value of alpha, I can put it into the equation number 1 and find out x dash, y dash and z dash. Now, let us consider that if the build direction is in plus z direction. In that case, if the build direction is plus z, nx will be equals to 0, ny equals to 0 and nz will be equals to 1. That means the unit vector in the direction of plus z will be nothing but 0, 0, 1. We know that. And the base on which we are building the part is xy plane, which is nothing but here. Therefore, your A will be also 0 in the equation of plane. Now, let us put all these values in the equation which we have derived, equation number 3, and hence your alpha will be equals to minus z. Now, again, let us use equation number 2 and find out the x dash, y dash and z dash. It will be obviously x dash will be equals to x because your nx is 0, ny is 0 and nz is 1. And now, we have just seen alpha is equals to minus z. Therefore, your x dash equals to x, y dash equals to y and z dash equals to 0. However, we have considered a very simple case when the build direction is plus z. In some cases, like when you deal with DED type of systems, the build direction may not be along the vertical axis. As the build direction may change, that is why we just derive a generic equation and consider now a specific case when the build direction is plus z. So, you can easily see if you have 3 points P1, P2 and P3, their projection on the base can be obtained just by replacing z by 0 and rest x will be x. So, for example, if P3 is x, y, z, then of course P3 dash will be nothing but x, y, 0. In a similar fashion, P2 dash and P1 dash. But please remember that it is true only when the build direction is in plus z direction and your base is aligned with xy plane. Now, let us try to find out the volume of the support which we are generating. if this is ith triangle and this volume which we are trying to find out is represented by Vi, that is the volume corresponding to the ith triangle support. Hence, the support volume of the support for the entire object can be given by I equals to 1 summation for all the triangles, that is the number of triangles. Vi equals to summation I equals to 1 to n Ai into Hi, where of course n is the total number of down facing facet of STL file. Those required the support. All the down facing triangles may not require support. So only those down facing triangles, those required support, that is represented by n here. Ai is the projected area of facet I onto the horizontal slicing plane, and Hi is the average support height evaluated from the corresponding facet to either the platform or to the next intersecting facet, whichever is less. Now what is the meaning of this? So for example, if you are building an object maybe like this, in this direction, these are the facets, those are having downward normal, and also these are the facets, those are having downward normal, and assume that they all need support. In that case, this support generated for these triangles will be projected on the part itself, while for these triangles the required support will touch the base. Therefore, we have mentioned Hi is the average support height evaluated from the corresponding facet to either the platform, if for example this one is going till the platform, or to the next intersecting facet, those are here for this particular support, whichever is less. Let us now just look at some nomenclature for the support mechanism. This is our part. The green color one is the support everywhere, and this black color one is nothing but the substrate or base, or sometimes also called as platform. Here you can see the support is projected on the base because it is going till the base. But in this portion the support is going up to the part. Therefore, it is called as support projected on part. In a similar fashion, here also the support is projected on the part. While there is a region which is having the downward facet normals, there is a region here which is having the downward facet normals, but in these cases the facet normal is not sufficiently downward, which required really the support. It is sometimes also called as self-supporting region because this is an overhang, but it doesn't really require the support. Now I'll show you one example of the support generated in a commercial package, and here you can see that these overhanging features require the support, and the support is projected on the part. So this particular support is projected on the part. While look at this support here in this zone, the support is projected till the platform or base. Hence, this is the support projected on the base. In a similar fashion, you can see these are the some supports, those are projected till the part only, and these are some supports projected on the platform. Now let us try to solve an example. The question is, the build direction of the object shown in this diagram is in plus z direction, and the support is required for the facet normals having angle greater than 120 degree from the build direction. Means if this is the build direction, this is the plus z build direction, and if there are facets, those are tilted like this and having the facet normal in this direction, and this angle I am talking about, this is theta. If this is greater than 120 degree, then only the support will be required. Determine the projected area of the support required for the given facets. Also, we have to ignore the base support, which is required to support the entire base. Second part of the question is, how many triangles you will examine for support calculation. Also highlight locations of these triangles. As by just looking at the drawing of the object, you can identify the zone where the support is really required and the zone where support is not really required. So of course, these are the critical zone 1, 2, 3, 4 and 5. Also, it is said that we have to ignore the base support. That means these facets are going to be directly in contact with the base. Hence, let us avoid or ignore these triangles because they are anyway going to support by the base. Now, these are the 3 zones or 3 regions. So now these are the 3 regions where we can see or examine the requirement of the support. Of course, this is the horizontal one and this is the downward facet normal. This will require the support mechanism. While let us look at this slant edge, it is making an angle of 30 degree. That means the facet normals for this will be having 150 degree angle from the vertical, which is of course greater than the threshold given, that is 120 degree. However, if you look at this, which is this face, the facet normal for this will make an angle of 120 degree from the build direction, that is your plus Z direction. In that case, support may not be required for this particular zone. Hence, the support will be required for this zone and only for this zone. Let us have a look at the 3D CAD model of the same. Here you can see this triangle we are not considering because they are directly attached with the base. These 2 triangles we are ignoring because the facet normal of these 2 triangles are making 120 degree from the build direction. Now the remaining triangles which are of our interest, those requiring the support, are this triangle, this triangle, this triangle and this triangle. So total 4 triangles are of our interest now. If I have the ASCII format of the STL file, then I can easily look into its code and I can identify the triangles those are having the facet normals making an angle of greater than 120 degree from the build direction easily. These triangles can be identified by looking at the Z component of the facet normal. If the Z component of the facet normal is lesser than 0.5, then of course the facet normal will require, or that particular facet will require the support mechanism. So it can be seen here also, if NZI is less than cos alpha, support will be required. What is NZI? It is nothing but the Z component of the facet normal of ith triangle. Now if our threshold is 120 degree, then if this Z component of the facet normal is less than minus 0.5, the support will be required. As we have ASCII format in front of us, we have chosen those triangles, those are having the Z component less than minus 0.5. So there are only 4 such cases. There is one triangle which is having exactly equals to minus 0.5, but we have to ignore it because it is not coming beyond the threshold value given, that is this particular face. So 2 triangles were during along with this particular face. So we will not consider this. So only these 4 triangles will be considered and we will find out the projected area only for these triangles. As the build direction is plus Z, it is very easy for us now to find out the projected points on the plane. These points will be nothing but X, Y and 0. We will just replace the Z component by 0. Therefore, everywhere wherever Z component is there, we will replace it by 0. This will give us nothing but the projection of this triangle on the base which is perpendicular to the build direction, and build direction is plus Z. So all these terms are going to be 0. Therefore, you will have the 4 vertex, those will look like this: 80, 0, 0. So let me draw that point correspondingly: 80, 0, 0. Then 50, minus 10. So 50, minus 10, assume it is here, and then 50, 0, 0. So this is the projected triangle. In a similar fashion, we can do for all the vertices. Now this is 80 comma minus 10. So this is 80, this is minus 10, 80 comma minus 10, then 50 comma minus 10 and 80 comma 0. 80 comma 0 is here. That means this is the triangle. Similarly, the third triangle will be having 3 vertices, 50 comma 0 comma 0. So 50 comma 0 comma 0 here, then 30 comma minus 10. So this is 30 comma minus 10 and 30 comma 0 comma 0. Therefore, the triangle will look something like this. The fourth triangle, the projection of fourth triangle will be 50 comma minus 1. So this is 50 comma minus 1. Then 30 comma minus 10. So this is 30 comma minus 10 and 50 comma 0. So this is the projection of fourth triangle. You can easily find out the area of these triangles by using this formula, we know that, or you can directly find out by using the half of base into height, because it is easy for these triangles to find out by using this formula also. Once you get it, for each triangle you can add the area for each and every triangle, and hence you will have the total projected area on the base. If it is required to find out the volume, then you can multiply the projected area, the summation of all the projected area, in that case we have 4 triangles, into the average height. This projected height can be calculated by the z component of the 3 vertices and by taking their averages. Now let us discuss about generation of support by the contours. In this method, first the contours are generated by slicing the entire object. Then these contours are used to generate the support structures. There are 2 popular methods of doing it. One is called as contentment and another is optimal method. The contentment method says the area to be supported is determined by projecting all the contours on the plane and then merged to get the external support. This big contour is then subtracted from the contours at each slice to determine the internal contours for support. So basically, if you have a CAD model like this, we do the slicing of the object and get the intersecting contours. How do we get the intersecting contours? We will learn soon in the next lecture. But if you have those contours, can be utilized to generate the support. These are some slicing planes, and if you take the intersection between these planes and the object, you will get contours. So as per the contentment method, for example, to understand better this method, let us consider an example. For example, we want to build support structure for realizing this bone in this direction. So this is the build direction for this bone. Like it is said, first we will consider the intersection between the slicing plane and the bone. And the intersection between the slicing plane and the bone will give you nothing but the series of contours like this. Now the next step is project all these contours on the base plane like you are seeing here. It is very easy to do because each contour will be consisted of some points, and these points will be having x, y and z coordinate. If I am projecting these points on a plane which is xy plane, then I need to just replace the z coordinate by 0, and hence all the contours will be projected like this. Then we need to use a marching algorithm to identify the outer contour. That is what you are seeing here. Then this particular contour, which is nothing but a bounding box. Now this big contour, which is nothing but the bounding area of this bone, is now projected upward like this. And each time a subtractive Boolean operation occur between this big contour and these small contours. So for example, let me consider a particular case, maybe here. the big contour will look something like this, and there will be a small contour inside. It says that in this zone you need the main material, while here you need the support material. In a similar fashion, you can build it up to the top. However, it is not a very optimal method because it can find out the support even those regions doesn't require the support. Therefore, another method came into picture which is called as optimal method. Let us now discuss about the support generation from contours. In this now we shall discuss the optimal method. In this method, first the contours are generated by slicing the entire object. Then these contours are used to generate the support structures. So this is how a sliced object look like. So this is the object which we want to use and to generate the support structure for this particular object when it is built in this direction. This is the build direction. So these are the slicing planes, and we take the intersection between the plane and the object. As a result, we get the contours. If this is the nth slice and this is the n-1 slice, corresponding to that, the contours are shown here. This contour is corresponding to the nth slice and this contour is corresponding to the n-1 slice. It can be observed very easily that after deposition of this slice, this region is going to be the overhanging region. While this portion here will be the supported region. By utilizing this analogy, now we shall discuss how we can proceed further to generate the support automatically. If these are some slices you are seeing here, these are some contours generated on different slices here. Assume that this is the nth slice, this is the n-1 slice, this is n-2th slice, this is n-3, n-4, n-5, n-6 and so on.